Welcome to lecture number 7 of electrical machines course. So we'll continue in fact that principles of electromechanical energy conversion. So last class we discussed about how the EMF is being generated, right? When a conductor is being moved in a uniform magnetic field, and what is the nature of the EMF, how it is pulsating, and the pulsating EMF we can collect it at the terminal through slip rings. And if you want a DC voltage, we need to use the split rings, right? Split slip rings. That is called commutator segments. So if we use it, then we'll get the DC EMF or DC voltage across the terminal, right? So in fact, we're continuing, and now in this class we'll see what will happen when a current carrying conductor is placed in the magnetic field, in a uniform magnetic field. So now we are talking about the uniform magnetic field. We are not talking about the varying magnetic field. So we'll talk in this class also what will happen when the varying magnetic field inside the varying magnetic field the conductor is put, and when what will happen. We'll see that, but before that let us see when a conductor carrying a current is in fact put inside the uniform magnetic field, what will happen. So before that already we have done this. Already you can see this. We found this. This is the maximum EMF that is generated 5p omega, and we have expressed this maximum EMF that is induced is 2 pi p. P is the number of poles by 120 5p nm. Nm is your speed of the rotation of the coil, that is in RPM, right? Rotation, revolution per minute, or rotation per minute, you can say. So this EC is nothing but the average voltage when we use the commutator segment. So this gives us the average voltage. So please mute yourself. So this average voltage I have told in the last class how to find, and we got it 2 by pi EM, and just substituting the value of EM here, we'll get substituting the expression of EM here, we'll get P by pi 5p omega n, omega m. So that is equal to P by 30 5p nm. Okay. So now we'll see the force on a conductor. So when a current carrying conductor is placed in the uniform magnetic field, then what will happen? Okay. So everybody knows this Lorentz law, right? Lorentz theory of force. We already you might have studied in your 12th class, right? So this is nothing but the force is given by equal to integration of I dl B. B is nothing but it is the magnetic flux density, and I is the current passing through this dl, elementary length of conductor. Suppose this is your dl and the current passing through is I. So this is ideal, and B is suppose downward here, right? Let us say this is B. Then your force will be obviously, this is the cross product of ideal into B. So the force obviously will be, please mute yourself. Please mute. Everybody I request to mute. So your force will be in this direction, right? So this will be force, right? That is perpendicular to the plane of I and B, ideal and B, right? Okay. So this is what the Lorentz theorem says, and just we'll use this for a conductor. We can see a conductor having length capital L, and the conductor is carrying a current I, okay, and the conductor is placed in the magnetic field that is B, okay. So this is the magnetic field B. Now I want to find the force. So the force is cross product of ideal. So here in this case dl will be L. So integration of dl will be capital L, right? So that will give me IL cross product B, right? So that will give me force will be equal to IL into capital B. B is the flux density, right? Now this is a cross product, so therefore it the force is a vector quantity. Now in which direction the force will be exerted, that will we have to see here, right? So now from the cross product we know we can find the direction, right? Whenever we multiply two vectors, suppose x into y, already you have studied in your physics, x cross y, suppose it is z. Now suppose x is in this direction and y is in this direction, right? Suppose y, x. Now what will happen to the cross product of x, y? So this is nothing but this is z. Z is nothing but it is the perpendicular to x and y, because x and y will rotate in this direction and the perpendicular on the plane of xy will give z, right? Already you know this from the physics, basic physics in 11th or 12th class, already you have studied, right? So now from this we can find this, right? Force will be ILB, the magnitude will be ILB, and if they are perpendicular x and y, sine theta will obviously 1, right? So then if sine 90 will be 1, and only we are worried about the direction. So the direction of the force will be perpendicular to the plane of IL cross B, right? So we can see here, this is your B and this is your current. This is your IL, right? Now this is your B, this is your IL, and so therefore your force will be in this direction, right? So this is force. Okay. So now we'll see this. This is one conductor. Now we'll place a coil inside the uniform magnetic field where the coil has two conductors, two sides, right? So there are two conductors. Now what will happen to that, to these two conductors? So this will be, the force will be ILB phi. So this will give the direction to us. Now this is called the motoring action when we place a coil. This is your coil, in fact, right? This is your coil which is placed inside the magnetic field, right? It has two sides. Let us say this is side A, this is side B. Okay. Now, so I have connected a voltage source and the current is being passed through the commutator segment to the conductor A and B. Okay. So now what will happen when, because the current will pass in this direction, because this is the positive terminal. So now the current will flow in this direction. This is I, right? Okay. So now what will happen to the force in conductor A? In which direction it will be there? The force will be, right? Let us see. So when this is the direction of I, so IL will be in this direction, right? This is IL and your field is in this direction, right? This is just downward. So this is downward field, right? So if they're perpendicular, your force will be in which direction? This is the cross product. Now this force will be here towards this parallel to, or parallel to this plane, right? Or perpendicular to this plane of IL and B, right? So now the force on conductor A will be in this direction, right? Now if we'll find the force on the conductor B, so conductor B, the current is flowing in this direction, right? That means in conductor B, the current will flow in this direction. This is your IL and your B is obviously here. Okay, I can say here, right? This is B. Now in which direction this will exert the force? So it will be here in this direction, right? So previously the force was in this direction in conductor A, and the force on conductor B exactly opposite, and therefore what will happen? The the force of both the conductor will be in the direction of rotation, right? So if we'll see, it will be in the direction. So therefore it will develop a torque, because when we have two sides and the force is acting on two sides in the opposite direction, then the coil will rotate, right? So therefore this coil will rotate in anti-clockwise, if we'll see, right? So the coil will rotate in anti-clockwise. Now let us see how we can derive the expression for torque. This is expression of force. Now this force on one side, the magnitude of the force in one side, conductor A will be IBL, right? And the torque will be, so because the net force will be 2Fe, so there, because at the two side both force is acting on, right? So therefore it will become 2Fe into R, right? R is the radius of the rotor, right? This is R, okay. So now it will become 2BILR. So your torque developed in the, that is electromagnetic torque, right? Electromagnetic torque developed on this coil, which is placed in the uniform magnetic field, will be this, right? Now the question is, if the commutator would not be here, suppose I put a slip ring here, two slip rings connecting these two wires, right? Then will it work or will it not work? So if I'll put slip ring, it will not work, because the force, whenever we can see here, the current will unidirectional in one conductor. It will not change, right? You see, when this conductor will move to this side, the current direction will change to this side, right? When conductor A will move to this side, towards the south pole, then the current direction will become opposite. At that time in conductor B, the current direction will be exactly opposite, which was in the under south pole, right? So therefore it will give a constant torque on A and B, so it will move, right? Constant force on A and B, it will move. But instead of commutator segment, if I would have put slip rings, then obviously the force, whatever it will be developed in the north pole at the conductor A, at the south pole it will exactly become opposite, right? It will oppose, and therefore it will oscillate. It will not in fact rotate, right? The rotor will oscillate, right? So that is what this commutator plays very important role. Okay, so now we'll move to a problem, a small problem. So after this problem, we'll go to the time varying field. What will happen to the coil when the coil is placed in a time varying magnetic field? Okay, so now let us see. So here the problem is the rotor of a 4-pole generator is wound with a 100-turn coil. So number of turns in the coil is 100. If the flux per pole is 4.5 milliweber, okay, so the flux per pole is given 4.5 milliweber, right? And N is 100. Okay. The rotor turns at a speed of 1800, that is Nm is 1800. Okay. Then determine the frequency of induced EMF in the rotor. Maximum value of, that is frequency F. The maximum value of the induced voltage, that is EM, right? Then the RMS value of induced EMF, that is EM by root 2, okay? And the average value of induced EMF is EC. That formula already we have derived, right? That is 2 by pi something else EM, right? So already we know this, and we have to just put this formula and find it out. This is very easy, right? Now if I'll find omega m, so I know omega m will be from Nm, it will be 2 pi 1800 by 60, right? And then F, the frequency of the induced EMF, will be 4 into 1800 by 120. Already we have seen this, right? So P by 120 into Nm, right? that is 60 Hertz. And then from F we can find omega. Omega will 2 pi F, right, radian per second. Now the maximum value of EM will be 2 pi P by 120 into 5P Nm, right? So that will give me 1.6965 voltage. So this voltage is in a single coil, right? Okay. So now I have 100 turns of coil. So therefore I will multiply it with 100. So it will give me 169.65 volt. So this is the maximum EMF in the coil, 100 turn coil, right? So now I will find the RMS value or effective value just by dividing root 2. I will find it will coming around 120 volt. And your average value will be 2 by pi EMC. So that will give me around 108 volt. So now the what you get from this problem is if we are connecting this machine as a DC generator, then we are getting a DC voltage of 108 volt across the terminal. This is the average value of the voltage, which is the DC voltage, right? And if we are using this machine as a AC mode, AC machine connecting the slip rings without any commutator. So with the slip ring, we are getting the RMS value of 120 volt and a pulsating wave whose maximum value or whose peak value is around 169.65 volt. Okay. This is a simple problem. Okay. So now let us move forward. So now we'll see a coil in time varying magnetic field. Okay. So what will happen when the one coil is placed in the time varying magnetic field? So previously we have seen that when you put a coil in the uniform magnetic field, just leave it, right? So we see no EMF will be induced because the flux is constant and the coil is, if the coil is placed standstill, it is not moving. That means the flux linkage is not changing, then the induced EMF will be 0, right? But now we have a time varying magnetic field. That means your magnetic field is oscillating, right? It is changing. That means whenever we will place a coil inside the time varying magnetic field, that means the flux linkage to the coil is changing. So when the flux linkage to the coil will change, then automatically the induced EMF will be produced, right? Okay. That means without any effort, without giving any external force, the induced EMF is being generated in the coil when we are placing it in a time varying magnetic field, right? So now the question is what kind of time varying magnetic field we can consider, right? Because in practice, most of the time we use the electromagnets. So electromagnet means we are exciting the magnet from externally, from external source. And we know we have the external source, existing external source is sinusoidal in nature, right? So whenever we are putting AC source in the coil, right, you're injecting AC current in the coil, that will produce a magnetic field, right? And that magnetic field is pulsating, will pulsate with it will pulsate along with the current, right? As the current will pulsate. So therefore only we can have in practice this sinusoidal time varying magnetic field. Okay. So now we can see here few facts. We'll take it and we'll understand this. So because this principle of time varying magnetic field is being used uh, in the machines like induction machines, right? Induction motors, induction generators, right? So when the starter winding of a polyphase induction machine are connected to a polyphase supply, they produce a revolving magnetic field. We'll see this how it will produce a revolving magnetic field. Okay, when it is a polyphase supply and it is given to the winding, right, starter winding or distributed winding of a induction motor, then it will produce a revolving magnetic field. And the strength of the revolving magnetic field is constant. We'll see all these things. Just I'm showing you some facts, then we'll analyze these facts. Okay. Then the field rotates a distance covered by two poles for each cycle, right, of the input waveform. Okay, so now the field rotates a distance covered by the two poles for each cycle of the input waveform. The force acting on the conductors of the coil wound on the rotor causes the rotor to rotate in the direction of the revolving field. All we'll see, right? So the rotor turns at a speed lower than the speed of the revolving field. And when your induction machine will be taught by Professor Siva Subramani, it will be in detail. And now I will just brief you how this revolving magnetic field will produce and how it will in fact rotate the coil without any support, outside support. The coil inside that revolving magnetic field will automatically rotate, right? And that is called induction motor. So just I'll introduce it, not in detail, just I'll explain the theory behind this, and in detail of the induction motor will be taught by Professor Siva Subramani, right? So we'll go now. So now I can see here we have three distributed coils. We can see here three distributed coils. Those are producing the magnetic field, right? You can see here one coil is here, S1, and is connected to S. Now we have another coil which is put here from S2 to F2. So S2 is having number 2. It is marked as number 2 and 2 dash, right? So it has two coils connected in series, 2 and 2 dash, right? And similarly, here we have 3 and 3 dash. So what we are observing here, that these three coils are distributed. How it is distributed? If we'll see the axis of these coils, we can see this is the axis of coil 1 dash, right? If just I put the axis, this will be your axis. Okay, 1 and 1 dash. Okay, or if we'll put the magnetic axis, let us put the magnetic axis. Now these two coils will produce flux, right? One will suppose during the increasing of the current, right, when the current is in a positive half cycle, right? So what will happen? This will become your north pole and this will become your south pole. Okay. So now your magnetic field direction will be here in this way, right? And now for coil 2, if we'll see, coil 2 is placed like this. So in this fashion, this will be here, right? And coil 3 will be here, somewhere here. Now we can see the axis, magnetic axis of these coils. If we'll see this is your 1, 2, and 3. Now what we are observing here is 2 is lagging 1 by 120 degree, and coil 3 is arranged in such a way it is lagging, the magnetic axis is lagging 120 degree by coil 2 or plus 120 degree from coil 1, right? Okay, so that means these coils are 120 degree distributed spatially, right? In the space of the stator or space of the some core, it is distributed 120 degree apart, right? Now this is the condition that the windings should be distributed, or if it is not distributed, then it cannot produce a revolving field. So now the winding is distributed 120 degree apart, right? So now we'll see, we'll go ahead. So we'll inject the current. Now we have currents, and let us erase this. So now we have the three-phase supply. To this three-phase winding I will feed. So first is I1. I1 is Im sin omega t. I2 is Im sin omega t minus 120. I3 is Im sin omega t plus 120. So these three sources I will feed to three coils. So I will feed one I1 to 1 and 1 dash, right? So S1 and F1, and I2 I'll feed at S2 and F2, and I3 I'll feed at S3 and F3, right? So now what will happen? So through the when I'll feed these currents, some flux will produce, right? At 1, 2, 3. And this flux, the nature of the flux will be exactly like the nature of the current because it will follow the current. Whatever way the current will flow, the flux will also like that it will produce, right? Exactly like same nature. So therefore, this is the current waveform, I1, I2, and I3, right? Now if we'll see the flux, so your flux will be exactly, if you suppose I'm writing here flux equation, your phi 1 will be phi m sine omega t, and phi 2 will be phi m sine of omega t minus 120. Then phi 3 will be phi m sine of omega t plus 120, right? Okay. Exactly when the current will pulsate, this flux will also pulsate in these fields, right? These coils, right? So now this is your current pulsation. You can see here I1 is pulsating like this according to the equation, and I2 is lagging by I1 120 degree, and I3 is lagging 120 degree to I2 by 120 degree, right? So now let us consider one instant. So at that instant, let us find the resultant flux. What will happen to the resultant flux, right? So let us consider one instant, that is instant 1, where let us say that is at the omega t equal to 0. At that point, I will evaluate the resultant flux. What will be the resultant flux in the total in these three coils? Because three coils will produce some flux, and what will be the resultant flux in these coils? Now these are the three currents, okay, at omega t equal to 0. And similarly, your flux will become phi 1 will become 0, phi 2 will become similarly, it will become minus of 0.866 phi m, phi 3 will be 0.866 phi m, right? Now let us plot this flux, okay, in the windings. So now we know phi 1 is 0, therefore phi 1 is not mentioned here. So now if I'll plot phi 2, so phi 2, I2 corresponding to I2, it will be exactly opposite. So therefore I can plot it like this, right? So your phi 2 should be, in fact, if it is positive, it should be in this direction, right? But as it is negative, so I am plotting it in this direction from 2 to 2 dash. It is negative, so therefore it is 2 to 2 dash. And whereas in phi 3 is positive 0.866 phi m, so it is positive, so therefore it is plotted from 3 dash to 3, right? That means from north to south. This is your south, this is your north, right? So phi 3 will be plotted like this. Phi 2 is opposite to whatever exactly in under positive condition, right? Now if I'll see the resultant, so phi 2 and phi 3 they will obviously make an angle of 60 degree, because if we'll see here, it will make an angle of so this will make a 60 degree angle, because obviously if we'll plot it here, so phi 1, phi 2 and phi 3, they should, this is your phi 1, sorry, this is your phi 1. Let's just I'm just plotting generalized phi 1, this is phi 2 and phi 3, so they're 120 degree apart, right? And when it will be opposite, it will make an angle of 60 degree with phi 3, right? Because here it is phi 2, so therefore it will be 60 degree, and the angle between minus phi 2 and phi 3 will also become 60 degree, right? So therefore phi 2 will make, minus phi 2 will make an angle of 60 degree with phi 3. So now because phi 2 is opposite now, so therefore it is making an angle of 60 degree with phi 3. Now if we'll find resultant flux, this phi r, so how much it will be? Phi r will be phi 2 square plus phi 3 square plus 2 phi 2 phi 3 cos of 60 square root. So that will give me 1.5 into phi m. Okay. Now the conclusion is that at instant 1, that is when omega t equal to 0, we are finding the resultant flux which is lying in this direction, and the magnitude of the phi r is 1.5 phi m, right? Now let us consider another instant, that is instant 2, when omega t is equal to 60 degree. So that means 1/6 of the cycle later. So first we took at the initial point when omega t equal to 0. Now I am taking at omega t equal to 60. Now if I'll evaluate I1, I2, I3 at omega t equal to 60, this I1 will become 0.866 Im, I2 will become minus 0.866 Im, and I3 will become 0 because sine it will become 180 degree, right? 120 plus 60, it will become 180. So sine 180 will be 0. So now if we'll plot the flux, respective flux corresponding to I1, I2, I3, because I3 is 0, so phi 3 will be 0, and phi 1 will be 0.866, sorry, 0.866 phi m, and phi 2 will be 0.866 phi m. It is minus, right? So now your phi 1 will be in the direction of from 1 dash to 1, right? It is phi 1. Now phi 2 will be in opposite direction, so I can plot it from 2 to 2 dash. So this will be here phi 2. Now obviously it will make an angle of 60 degree with phi 1. Now if we'll find the expression for resultant flux, that is at instant 2, the resultant flux will be phi r2 will be phi 1 square plus phi 2 square plus 2 phi 1 phi 2 cos of 60 square root, right? Again, if I'll take this, I'll find 1.5 of phi m. Okay. The same thing you will get again here, right? So that means phi r2 is becoming 1.5 phi m, but it is shifting an angle of how much? It is shifting an angle of 60 degree, right? That means when we are taking the instant when omega t equal to 0, that means we are changing the supply, or we are evaluating the resultant flux at omega t equal to 60 degree. Your flux is also, the resultant flux is also rotating. Previously your resultant flux was here, right? In instant 2 your resultant flux was here, and at omega t so this is at omega t equal to 0. Now when I make omega t equal to 60 degree, your resultant flux is moving also 60 degree, right? Okay, it is making an angle of 60 degree with phi r1. So it is also moving an angle of 60 degree, but the magnitude is remaining same, right? The phi r1 equal to phi r2 equal to 1.5 phi m. So the magnitude is remaining same, whereas the angle it is making with another 60 degree to phi r1. So that means it is rotating with respect to the change in the change in flux, right? When the flux changes with time, your net or your resultant magnetic flux is also changing its position around the circumference, right? So it is now rotated by 60 degree as your supply frequencies, as your supply is pulsating or moving towards 60 degree, right? Okay. So now this phi 2 is 1.5 phi m. Now let us consider another instant, that is instant 3, where your omega t is equal to 120 degree. Okay. So now when omega t equal to 120 degree, that means it is 1/3 of the cycle later. So we are going ahead, right? So the currents in the 3 phases will become how much? Your I1 will become 0.866 Im. So you can take any instant, you can evaluate, that is not an issue. But I am taking certain instances at which we can do hand calculation, right? So if you have a calculator, you can take instants like omega t equal to 90 degree, omega t equal to 45 degree, omega t equal to 30 degree. Any instance you can take. Your resultant flux will remain same. The magnitude. Only the angle of rotation of the resultant flux will change. Okay. So the resultant flux magnitude will remain at 1.55 m. Okay. And now for this instance also, if we'll find, so corresponding to these currents, your flux will become 0.866 phi m, and here your flux will become 0. Here your flux will become 0.866, sorry, 866 phi m. Now if we'll plot this flux, and again you find the resultant flux at instance 3, that is phi r3, we'll find also it will become 1.55 m. Whereas it will rotate an angle of 60 degree. That means it will make an angle of another 120 degree with respect to the original position, what is here, right? This is your phi r1. Now it is making an angle of 120 degree with respect to phi r1, that phi r3, right? That means as we move, as your the evaluation instant will move, your resultant flux will also move, right? That means when you're for a pulsating current, we'll get the pulsating flux, and we are finding a revolving resultant flux which is revolving with respect to the pulsation of the current waveform or flux waveform, right? With a constant magnitude, that is 1.55 m, right? So now we can conclude from here that when there is a three-phase or three-phase pulsating or the pulsating magnetic field because of the three-phase current, that in fact produces a revolving magnetic field, right? That the magnetic field rotates with a constant magnitude along with as the in accordance with the current waveform, right? Okay, so that means your resultant flux is moving, right? It is rotating with respect to the current waveform, right? As the current waveform moves, your resultant flux also rotating. So this is the conclusion. Now if we'll see the what time it takes. Now we can see here before moving ahead, we can see here that each of the winding for each phase, right? So this is making one pole pair, right? That means I can say that here is one pole, right? This is, suppose I will mark it as north pole, it is south pole, or it is north pole, it is south pole, right? Now this is making an north south. So we can see here there are two poles in each phase, right? That means one pole pair in each phase, right? So I can write here that there are two poles per phase. Okay, per phase. Similarly, if I increase the number of poles per phase, suppose I can make it 4 poles per phase or 6 poles per phase. So that means your rotation will vary accordingly, right? It will cover half of the time, right? Half of, suppose I'll take 4 poles per phase. So this resultant flux will move only 180 degree with 360, one cycle of the supply, one cycle of the current. So with respect to one cycle of the current, this resultant flux will move only 180 degree, right? That means half of this. Okay. So therefore, if I'll find the time required by this flux to move, right? If your t, capital T, is your time period of the current waveform, that means your t is 1 by f, then I can write the time period of the rotating flux. It will be p by 2 t, capital T, right? So if Ts is your time required or time period, you can say time period of rotating flux. So what it means? It means the time required by the rotating flux to uh, complete the cycle, right? So complete the whole circumference of the rotor, right? So that is time period of the rotating flux. That means from where, suppose your rotating flux is starting from here and it is moving, and when it will come to here, right? It will come and arrive here. The time required by this rotating flux to arrive here to the original position is known as the time period of the rotating flux. So we have seen for a two-pole machine, two-pole per phase machine, so it is exactly equal to T, right? So if you increase the number of poles, let us say there is a machine with poles, so P poles per phase, then what will happen to the time period? It will become P by 2 into capital T, which is the capital T is the nothing but it is the time period of the current waveform. Okay. Now this is time period of the current waveform. So now what will happen again? So let us erase it. Now your speed will become, that means your speed of the rotation, that means revolution per second. The speed of rotation of the rotating flux will become 1 by Ts, right? So it will become 1 by Ts because it is rotating for one revolution, it is taking Ts second, and for ns revolution it will take, so sorry, for in 1 second how much it will revolve? It will revolve 1 by Ts, right? Ts revolution. That means in 1 second the flux is rotating 1 by Ts revolution. Okay, that means I can write it ns, that is revolution per second. I can write it as rps. So that means rps of the flux will be nothing but 1 by Ts. Okay. And that I can write it equal to just substituting Ts p by 2 T. So I can write it as it will be 2F by P, right? Okay. So it will become 2F by P. And further, I can write this revolution per second. If I'll convert it to revolution per minute, then what will happen to it? That is RPM. We call it RPM, revolution per minute. So I can easily convert revolution per second because Second is nothing but 1 by 60 minute. Just I'll substitute 1 by 60. It will become 120 F by P, right? Okay. So now your NS, that means the speed of the rotating flux, that is in RPM, will be 120 F by P. And P is the number of poles per phase. Okay. And now I can convert this to omega s, that is angular speed. Omega s will be 4 pi f by p. So that is nothing but 2 by p omega. Okay. So omega is the angular speed of the current. Okay. Angular frequency of the current. Okay. Now this up to we have seen how the rotating flux will be produced in a coil which is placed uh, in the magnetic field, right? And when this flux is rotating and it is linking the coil, what will happen? So there will be change in flux linkage in the coil, right? Suppose let us say this coil is placed in that rotating flux. This is your revolving field, right? This field is revolving in this direction, right? Let us say, right? And here we have a coil. This is your coil, right? Marked as nothing is marked. Let us mark it as A dash, right? Now, as this coil is put inside the revolving field and the field is rotating, so therefore this coil will experience a change in flux. When this coil will experience a change in flux linkage, then obviously this coil will produce, or there will be an induced EMF in the coil sides, right? So this coil will have an induced EMF, and therefore if the coils are closed, right, the coil terminals are closed, that means both side the conductors are sorted. That means I'll put, this is your coil side, and if I'll sort at both the side, at both the end, if I sort it, right, then it will make a closed path, right? Whenever the EMF will be induced, there will be a flow of current inside this, right? So as the current will flow inside this closed loop coil, right? So then what will happen? Then there will be force, that will be the induced flow force will be there in this conductor, right? Okay. So there will be induced force on these two conductors. So we are seeing that because of the revolving field, there will be a change of flux in the coil, this closed coil. And because of this change in flux, we have a current inside this coil. And because of that current, we'll have a force induced on the coil side. And that will rotate this coil. Okay. So now this coil will rotate. Okay. Suppose. So now the question is at what speed this coil will rotate. And at what speed this coil will rotate. So this coil, if suppose, let us say the coil will achieve the speed of a rotation at which the revolving field is rotating. Let us say your revolving field is rotating at ns and your coil started rotating in such a way that it achieved the speed of the rotating field. Then what will happen? If it will achieve the speed of the rotating field, then there will be no change in flux linkage in the coil, right? So there will be no change in the flux linkage in the coil. So therefore there will be no current in the closed coil, closed path of the coil. So therefore there will be no force again. So when there is no force, then what will happen? It will retard, right? Gradually it will retard. When it will retard, again there will be a change in flux linkage, again the flow of current, again there will be torque on it, and again it will rotate. That means this coil will rotate in such a way that it will always lag behind the rotating flux. It will never achieve the speed of rotating flux. It will lag little bit, not far, right? So if rotating flux is rotating at ns, then if your coil is rotating at nm, so therefore we can say that your nm will be always less than ns. Okay, it will never achieve the speed of ns. Whenever it will achieve, it will again lag behind, right? Because the torque will reduce on the coil, right? So therefore, it will always lag behind. So therefore, if we'll say that nr is the speed of the rotor where the coil is placed, and ns is the speed of the rotating or revolving field, magnetic field, then sorry, nm is the speed of the rotor where the coil is placed, and ns is the speed of the rotor, speed of the revolving field, then I can say that the relative speed between the rotating flux and the rotor will be ns minus nm, and this is known as slip speed. Okay, so in technical term we call slip speed because the rotor is slipping behind the rotating flux by this much of speed, nr. Okay, therefore it is called slip speed. Okay. Similarly, if I'll convert this slip speed into angular velocity, it will be omega s minus omega n, omega m, right? Now another term is defined here that is called slip. Slip is nothing but the relative speed between the rotating magnetic field and the rotor speed, right? That is, sorry, that is the speed of the rotating magnetic field. That is the synchronous speed. So that will give me the slip. So slip, I can write it omega s minus omega m. The relative speed is omega s minus omega m by omega s, right? So if I'll write the speed of the rotor in terms of the slip and the speed of the rotating field, I can write it as 1 minus s into omega s. Just adjusting this equation, you will get this equation. And again converting it into RPM, I will get Nm, I will get equal to 1 minus s into ns. So where Nm is your speed of the rotor where the coil is placed, and s is your slip, that is the ratio of the relative speed to the speed of the rotating field, and ns is the speed of the rotating field in RPM. So this is in RPM, this is in radian per second. Okay, the units are important, right? Sometime we also mention in RPS, that is Nm equal to 1 minus s into ns. Okay, so this is what all about. So this is a very small problem. We'll take it in the next class because we have we are now short of time. So you have to also attend the other classes, and I will take only few doubts if you have. Okay, so now I will take few doubts. Thank you very much.